one would objectively curate these kinds of models. So if you have models coming from a single kind of experiment, then it's easier to come up with objective ways to say how good the model is. But when you have multiple sources of information and where you weight each experiment differently, how do you come up with an objective way of saying this model is good and another one isn't?
Yes. So it's an excellent question. It's very important. It's as important, maybe more, as the question, how do you get the model? It's maybe more important to quantify the uncertainty of the model once you have it. The modeling subgroup of the protein data bank that I happen to lead has in fact 3 goals. One is to create a representation of integrative structures that will be very general and very broad. And we largely achieved that. That's why the PDB site already exists. The second goal is model validation. That's your question. The third one is model validation, but the second one is model validation. What is the protocol that should be applied to all integrative structures as part of the position eventually, so that we estimate the uncertainties and live with them properly and not be either too optimistic or too pessimistic about it. And there is a starting point for that protocol, but we are far from agreeing or finalizing it. Nevertheless, I can say maybe a couple of things. It's currently proposed to be a series of steps. The first step is a test of whether or not the sampling of various alternative models was performed with the precision that is at least as good as the precision someone claims for the final model. If that's not the case, you cannot claim that precision. But you can assess the precision of your sampling in the cases when you're using stochastic sampling method by repeating stochastic sampling many times independently from different starting configurations, for example, using different random number generated seeds and so on. And showing that if you do this a large number of times, you stop finding new different solutions. It's a statistical test, so you can never be completely sure. There could be some funky landscape shapes that will mislead you in this test. But it's a reasonable test. So that's the first step. Once and only once you are passing that test, you start asking, do I satisfy the data used to compute the model? And in this test, you go data point by data point independently. In this test, you will rely on an assessment of the uncertainty in each data point or in each data set. And for that, you will have to rely on what the experts on this data tell you. And so there is in fact this other, for that, not only for this reason, but significantly for this reason, a second working group in the protein data bank, which is about the federated archive. And it's a federated archive because it will contain not just the structures and the protocols, but also the data that were used to construct the models that currently are not archived yet. Chemical crosslinks, all sorts of spectroscopies, the field propagation experiments, and so on. So there are efforts in these various archives ongoing. They're nascent efforts, so not too many have been finalized yet, that will produce criteria and methods for validating the data. So we will know, the modelers will know what the uncertainty of the data is in each specific case, and therefore we'll be able to judge much better whether the deviation between the model and the data is significant or not. So that's going to be a part of the second step. The third step is assessing a model by cross-validation types of approaches, where you take the subsets of data out that were used initially and repeat the calculation without these subsets, compare the resulting model against both the original model and the omitted subsets of the data, And just using the traditional cross-validation types of considerations, you will, in this way, assess, as we discussed, I think already, both the model and the data. But now you'll be able to do it better because you will have better estimated uncertainties in the data from the previous effort I mentioned. The fourth step may be very similar, but using the data that actually were not used to compute the model at all. Other than that, very similar. The fifth step might be using so-called toy models, where you take the structure as correct by definition, you simulate the data of the same type as best as you can, trying to reproduce the actual data as best as you can, and then recomputing the model with the simulated data. But now you know for sure by construction what the native state is in this toy universe in which you are the master. And therefore, you may be able to gain experience about what kind of data, of what quality are required to obtain a certain level of precision and accuracy. And many current traditional assessment criteria, say for crystallography, are like that. You know, the 2 angstrom resolution of an X-ray structure through experience, a little bit the Lozada plot, implies a 10 times smaller uncertainty in atomic positions. That's experience-based to a large degree. So similar types of assessments can be imagined for integrative structures. And then there is finally, well, then there may be certain ways through the if we express all the data in a Bayesian fashion, we will be in a stronger position to use the Bayesian logic to talk about uncertainty in the model. And I'm not elaborating on that, but there is that option. And then as the final point, you will kick me out inappropriate, right? As the final point, like you asked the question, as the final point, I think there is a possibility to increase our confidence in models, structural models, and everything is a model, even X-ray structures are a model, to increase our confidence in the model based on the ability of a model to explain something that wasn't conceivably or convincingly explained before, or that is consistent with something that you wouldn't expect, but after the fact it appears in the model. It's very abstract, but let me give you an example. In the case of the nuclear pore complex, we knew about the 8-fold symmetry in the ring just from the composition and electroscopy. But if you look at the structure or model that we computed based on all kinds of data, there is a 16-fold symmetry, not 8-fold. And there's no reason to expect the 16-fold symmetry. It wasn't in the input, yet it appeared. What are the odds that it would appear by chance? Low, right? So if it did appear, I would have a higher confidence in the model based on the supposition that there is in fact a 16-fold symmetry, and you got it in the model indirectly through some kind of synergistic effects of all the restraints combined. And have more confidence when that happens in the model than when it doesn't happen. And there's other examples of that you can imagine. And it is another maybe wishy-washy a little bit type of validation, but at least the sign that it's good or bad is clear.
Okay. If it's a quick question,
That's a long one. So I have 2 questions. First, how do you get the prior distribution? How exactly do you get one? And second is that suppose you predict a structure from your model and it's not very accurate. Then you go back and change your scoring function.
Yes.
But then how do you avoid overfitting the data?
Yes. So you have several different questions, all of which are great questions. My favorite color is the same as yours, blue. On the accuracy question, I will say we never know what the accuracy of the model is. because in order, as accuracy is defined as the difference between the true structure and the model. We don't know what the true structure is. If we did, there would be no reason to compute a model. So we have to admit that you can only guess about the accuracy. However, what you can estimate without guessing is the precision of the model. And then you can say that the accuracy is not very unlikely to be better than precision. Right? The precision is the lower bound in the accuracy. The precision you estimate simply from the variability among the independently calculated models, all of which are equally good satisfaction of the data. And there was another part of the very end,
Overfitting the data.
yes, overfitting the data. That's a very good question because it allows me, hopefully, to shed some light on an important aspect of modeling. And people will often criticize modelers for overclaiming what the model is. They say, how can you determine the values for 1,000 degrees of freedom when you only have 10 data points, approximately speaking? There was a question along these lines already, right? But you're not, in this approach, proposing a single model. We're proposing an ensemble of models, each one of which could be a solution. And therefore, your data to parameter ratio, you have effectively a much smaller number of parameters because of that, because you're not suggesting, you're not requiring that you have a specific value, a single model, or each specific value for each degree of freedom, a single model in the output. I'm saying any one of them is an equally good representation of the data. So when you are suggesting all models, if you have your confidence in your sampling, you can do that. You're suggesting an ensemble of models that could be very different or very similar. It is what it is. That satisfy the data. You cannot overfit. You're not overfitting. You're only overfitting if you suggest only one or a small part of it. So that tells you you have effectively a solution to the overfitting problem. It goes away when you require an ensemble of solutions as opposed to a single one. And you don't know then if that's the only one or there's many others. I just said, these are all solutions, no overfitting, it's gone. A special case of that is, of course, when you consider the interplay between the sampling and scoring and your computer size and data precision and so on. You can reduce the representation resolution. And that's normally what people would require as a response to overfitting. And don't determine 1,000 coordinates. Simplify the system's description and determine only the positions of 3 domains. You have 10 data points in this example. You can kind of do that, right? That's another way, but it's more general if you can do it, to sample with sufficient resolution the entire ensemble, each of models, each one of which is expressed at whatever resolution is feasible, and considering patient efficiency and the nature of the data and so on. Again, a long answer, but it's a very good question. I have some clear.
Maybe I'll talk to you.
That's too.
To join me in thanking Andrej.